Hello, IBSL2. We are about to start calculus today, and what I want to make sure you guys see is there is a link that I want you to watch before you start the notes tonight. So what is calculus? It's only about a minute and a half long, and it gives you a pretty good description of the differences between what you guys have been doing in algebra up to this point, and then how we're going to take what you've been doing in algebra and start to take it a little further with our calculus. So go ahead and watch that first, and then you'll also see the second part of homework, which is going to be linked right below it in just a few minutes. So from the video that you guys watched, you should have a few notes here about the introduction to calculus. And what you guys started to talk about with that video is this idea of slope that you pretty much have been using ever since you started, about 7th, 8th grade math and Algebra 1 especially, right? So we have this idea of slope. So you might have been in 8th grade doing Algebra 1 or pre-algebra, and we talk about the slope between two lines, and they have to be 2 points. So you have to have 2 points in order to create a line. So we are talking about the slope between 2 points, and you have to be given what those points actually are. So my 2 points, boy oh boy, there we go. You have x1 and y1, and you're given x2 and y2. You guys have only seen this about 1,000 times, so I'm going to do that pretty quickly. Okay, once you have these 2 points, you can find the slope by taking the difference between the two y's, so the difference in your y's, y2 minus y1, and divide it by the difference between your x's, your x2 minus your x1. And that gives you your slope between 2 points. Now, notice I put a couple words over here on the opposite side. I'm going to use red to highlight them. What's the difference between the average rate of change, and then you have this word constant, and then you have this word variable, and instantaneous? These are all forms of rate of change. What are they? All right. Average rate of change is exactly what you guys have been doing since you started Algebra 1. I'll use this dotted line to show. If you guys have a linear equation, you take 2 points anywhere on that line. So let's say I take these two. My rise over my run, in order to meet the next point on the line, is always going to be the same. If I pick another point and I take my rise over my run, it's always going to be a ratio, the same exact ratio between any 2 points on the line. So we are finding an average rate of change, but it is constant. It is the constant speed that this line is either increasing or decreasing or staying flat, whatever the case is. The slope is constant. When you guys were in Algebra 2, you started to look at something called a parabola, or maybe a polynomial. So here we have a cubic for you as well. The only thing you did not talk about is really what the slope was. Because if you notice, if I try to take the slope between those 2 points, and then maybe the slope between these 2 points, if I found the slope just between those 2 points, notice how steep it is and in a negative direction. And then notice the distance between these 2 points. If I find the slope between those 2 points, that looks like a flat line, looks like a horizontal line to me. So I'm going to have 2 different slopes, but they're supposed to be the same slope for this one curve, right? Not the case. So you didn't talk about it in Algebra 2 because that's really part of what calculus does. It finds the slope along lines, or curves, that are not lines. So they're not straight. They do change. There are changes in direction. And that is exactly what we're about to get into here. So variable, meaning change, right? Constant, meaning not changing. And then we have this new word, instantaneous. And this is going to be our topic of discussion that I'll leave you guys with today, because that's exactly what we're going to practice next class. If you guys think of this, I'm going to add a little bit to this picture here. And this will be a very, very informal way to talk about this. And then we'll do it a little bit more formal in just a second. But let's say I say my y-axis is distance, and let's say my x-axis is time. As time passes, let's say this is distance over time of some kind of moving object. You can call it a car, you can call it a person walking, whatever you'd like to do. But let's say I'm coming down this way. I always read my graphs from left to right. My distance is decreasing as time is passing. Then I stay pretty close to doing kind of the same here. My distance is passing, or my distance is kind of staying the same as time is passing here. And then suddenly my distance starts to really increase as time continues to pass. If you think about it, would my speed, remember speed is distance over time, or y over x, it is your slope. If I took my average speed between these 2 points here, right? Look at that slope right there. It kind of seems very steep. And then I take my average speed between these 2 points here. Do you think that would be a good approximation for my speed along this entire curve? Do you think it'll stay the same? Probably not. Or what if I wanted to stop right here at this point and I wanted to find my speed only at this point? Like what was happening at this point? Let's say, I don't know, I want to know exactly the speed right here. So I'm traveling distance and time is passing and I get to right here. Okay, well, that's really hard for me to tell exactly what speed I'm going at this one particular point unless I do something with a slope. Well, instantaneous rate of change is going to allow us to find the slope or the instantaneous rate of change at a particular point. So that's going to be our last topic today when you guys are going through your notes. Just a little background before we get started. All right, so we are going to start with our average rate of change. I'm going to write average at the top so we don't forget what we are talking about here. This is exactly like Algebra 1. So I'm just going to put in parentheses here. Do not make this more complicated than Algebra 1 material. This lady, Koila, she's keeping track of the water consumption invoices for a 1-year period show. Okay, here we go. Over a 1-year period, in the first 3 months, water consumption was here. The second quarter, the next 3 months, was here. Third quarter was here, and the fourth quarter was here. The directions are asking us to find an average rate of water consumption per day for the first quarter. What would you do? So take a second if you need a pause. Try these, because I'm going to ask you guys to try these and bring your answers to class. But if you think about the first quarter, this is how much water was being consumed in the first quarter, and I want to know how much was being consumed on an average per day. Well, how many days were in the first quarter, right? I'd have to figure out how many days that was. And if I have my total, and I have the amount of days I want to find per day, well, then I would divide, right? My consumption divided by how many days were in the first quarter. First 6 months would be pretty similar. I've got my total consumption over the first 6 months, divided by how many days I have in the first 6 months. Very similar to the whole year as well. Go ahead and make sure you have 3 answers, and we'll check them tomorrow. Starting to move a little bit away from algebra and into calculus. I'm going to give you guys an example from our textbook. And this is going to start to open our eyes to why we even need to consider this in the first place. Here we have a motion, and our meters are on the y-axis, seconds, again time is on the x-axis. We're asked to find an average speed. Okay, remember average speed. Average speed is our distance over time. Okay, so if we have our distance, whoop, this thing loves to catch my letters here. Okay, distance over time. There we go. I'm going to set this up just like I would use the slope formula. In the first 4 seconds, I am right here, 0, 2. 4 seconds pass, and I'm now at 4, and I'll call this about 2.3. How would I find my average speed? I would take my distance divided by my time. I can already tell my distance is about 0.3 divided by my time, which is 4 seconds. If I wanted to write this out as in the slope formula, then I could use the 2 points, 0, 2, and 4, 2.3, and find the slope. I'm going to do the same thing in the last 4 seconds. From here, 4 to 8. Again, I can tell how much distances I've traveled, starting here and then moving up to here. Look at my y distance in meters, and then I've traveled again for 4 seconds. Go ahead and find the average speed between that 4 second mark and the 8 second mark. Then you're going to be asked to use the whole 8 second interval. So starting at 0, starting here, and ending at 8, what would be the slope? Go ahead and take a moment to do so. Once you finish, this is what you guys should be getting. So we took our y distances, the difference between them divided by the 4 seconds, and so on and so forth. You guys can double check me. But if you guys look up at the graph, look at how different those values are, and let's see what they actually do. So if I draw a line, because really when you guys are finding the slope between 2 points, you're just finding the slope of a straight line. So here we have from 2 to 2.3. Okay, so let's say I find the slope between those 2 points. I get 0.075. That is very close to being a flat horizontal line. That is apparently my slope. Then let's say I take the slope between the second set here. Well, that, I was getting something a little closer to 1, but that's a huge difference. And already in my picture, look at the distance between the straight line that I found the slope of and the curve that is actually representing the path of whatever this object is in motion. We already have a huge discrepancy between the line that we found the slope of and the curve that we're supposed to be approximating here. Then we have the average for all 8 seconds. So let's say I start here and here. All right, that's not quite as steep as the second one, so it's not quite close to 1. It's closer to a half. Well, I have 3 very different values here because they're giving me the average in those 3 different intervals. Well, none of them really represent. This one really is the closest. See how close that line is to the curve? That one is really the closest in representing what's happening with our motion here. But this second part is a little further away, and the whole straight line from 0 to 8 is missing out on a lot of what's going on in the first 8 seconds. So in order for us to get a better representation, as you can see from this first 4-second interval here, we want our points to be closer to the curve so that when we create a line, the line is closer to the curve. So what that's going to take us into is this idea of instantaneous rate of change. The rate of change of an object in motion at a particular moment in time. So we want to be able to eventually find the actual slope or speed of an object at one point instead of taking this huge interval and approximating it by finding the average. So I'm going to take you guys to your textbook. We are now in chapter 20 of your textbook. So the first several chapters were what you guys covered in SL1. We primarily focus on the chapters in the 20s. So from 20 till the end of the book, we work with your, that's all of your calculus chapters plus some more statistics. So a lot of things we'll go back to obviously and visit, but we start at chapter 20. You guys are given an example right here on page 514. So if you'd like to open your book and look at a few other examples, you can. But this is also distance and time, all right? Some object is traveling along this curve, time is passing, distance looks like it's increasing, right? I want to approximate, we're being asked to find the instantaneous speed at time of 4 seconds. So right here, that's what I would like to find the speed at. If I want to approximate the speed at 4 seconds, I'm going to need 2 points that are very close to 4 seconds. And I'm going to need to find 2 points that are really close so that when I make my line, they're also very close to my line, to my curve right now. So what you'll notice is, oops, went a little far. If you guys pick 2 points and you let them get really, really close to each other, well, if I have 2 points that are super close to each other right here at 4, really what I'm drawing when I connect my 2 points together is a tangent line. And remember from SL1, a tangent line is a line that gets really close to your curve, hits it at 1 point, and then it continues to go. So it only touches your curve at that 1 point, and that's the 1 point that I want to actually find my slope at. If I have 2 points that are super, super close, and they're so close to each other that really what I'm creating is a tangent line, then what I want to find is the slope of that tangent line. So for me, when I drew my tangent line here, or when the book did, when you notice, let's pick 2 points that are kind of easy to use. So 2, 0, that's an easy point. Again, this is the point on my tangent line, not on the curve anymore, because my tangent line is going to approximate my slope, or my rate of change, at when time is 4. Notice how our slope then, if you use the slope formula, will come out to 8 meters per second. Before you guys come into class tomorrow, try these 4 problems below the example on page 515. by drawing your slope at the point that it's asking